Okay, I want to do our first example of a differential equation where we genuinely need a power series representation. So this is not going to be a differential equation that we can solve. But what I want to do is I'm going to solve what's called Airy's equation. And this is the equation y double prime equals x, y. Totally innocent looking. Okay, it looks super easy to solve. It is not super easy to solve. Try it. See what happens. See if you can figure out how to solve this. It's not so it is second order linear, but it doesn't have constant coefficients. So all that stuff is out. There's no integrating factors or anything like that we can do. Yeah, I mean, there's really not many methods that we've talked about that can solve this problem, as simple as this problem is. And it turns out that this function, the functions that are going to be, we're going to have two linearly independent functions because it's a second order linear differential equation. But these two linearly independent functions are going to turn out to not have nice closed algebraic forms, right? And that is what it is. So this is, I think, maybe the simplest example of a differential equation. I need to be a little bit careful here, but this is definitely an innocent looking problem that's not so innocent. So we're going to do the usual stuff. Let's let y be the sum c sub n x to the n. So n goes from 0 to infinity. And then y prime is going to be n times c sub n minus 1. I might as well just do it. Y prime. So sum starting at 1 of n c sub n x to the n minus 1. And then y double prime is going to end up being the sum starting at 2. From 2 to infinity. And then we're going to have n times n minus 1 c sub n x to the n minus 2. And we're going to take our expressions for y double prime and y and plug them back into our differential equation. Okay, so our ODE is going to become, we're going to have the sum from 2 to infinity of n times n minus 1 c sub n x to the n minus 2. That's going to be equal to x times y, which was the sum c sub n x to the n. So n goes from 0 to infinity. And then this is going to be very similar to what happened in the previous one. We're going to have to put the x in the sum on the right. So we'll push that inside the sum. So this is the sum from n equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2. On the right, this is the sum from n equals 0 to infinity c sub n x to the n plus 1. Notice again that we have a discrepancy. We have this left sum starts with a constant term, right? You have x to the 0. This right term starts with a linear term, so we're going to have to do the same thing that we did before and peel off the n equals 2 term. And now when n is equal to 2, we're going to have 2 times 1 times c2 x to the 0 plus all the rest. So the sum from 3 to infinity n times n minus 1 c sub n x to the n minus 2. And that'll be equal to the sum on the right, which we haven't messed with now, c sub n x to the n plus 1. Now we're going to shift our index by 3 so that our powers of x and so that the starting index agrees. And so here this is going to be 2c sub 2. And the sum here is going to be the sum starting at 0. And all our n's are going to become n plus 3. So this is going to be n plus 3. N minus 1, if I change n to n plus 3, becomes n plus 2. C sub n plus 3, x to the n plus 1. That's equal to the sum n equals 0 to infinity c sub n x to the n plus 1. Okay, that's a c sub n. All right, and now we have, now everything is fine. If you like, and you don't really have to do this, I kind of like doing it. I'm going to put a 0 on the right side so that everything is really equal now. We have constants on both sides. And so this tells you that C2, 2C2 is going to be 0. And we know that these two expressions with the constants are going to be equal. So and n plus 3 times n plus 2 times c sub n plus 3 is going to be equal to c sub n for all values n greater than or equal to our starting index, which is 0. Okay, so that's true for all n greater than or equal to 0. Okay, so this tells us that our sequence C sub n plus 3 is equal to C sub n over n plus 3 times n plus 2. And our C sub 2 is 0. Our C sub 0 and C sub 1, we should just give names. So say C0 is A, C1 is B. We've already seen that C2 is 0. And then from here, we can just get the rest of the values. So C3 is going to be what happens when n is equal to 0. So this is going to be C3 is going to be the third term back, so C0 over 3 times 2. So that's A over 3 times 2. C4 is going to be C1 over 4 times 3. So that's B over 4 times 3. C5 is going to be C2 over whatever, because that's 0. C6 is going to be C3 over 6 times 5. So that's A over 6 times 5 times 3 times 2. There's not going to be, I mean, there's a pattern, but writing the pattern is kind of a pain, so we're not going to worry about it. Let's just find a few more terms. C7 will be C4 divided by 7 times 6. And then maybe 3 more. C8 will be 0. So no surprise there. That's a multiple of C5. C9 is going to be C6 times 9 times 8. And then C10 is going to be C7 divided by 10 times 9. Okay, and these values in the denominator are what they are. We don't have to worry about it too much. But rather than coming up with a closed formula, let's just simplify this. This is going to be A over 6, B over 12, A over 6 times 30 is 180. And let's see, 7 times 6 times 4 times 3 is 42 times 12. Let's just stop there. 42 times 12 is 504. So this is B over 504. Okay, so C9 and C10, you can figure out what the denominators are if you like, but that's fine. So now what we're going to do is notice that we have 3 different expressions. When your subscript is a multiple of 3, so namely when you're at C0, C3, C6, C9, you have an expression with an A in it. For C1, C1, C4, C7, C10, so in other words, multiples of 3 plus 1, you're going to have an expression with a B in it. And then if you have multiples of 3 plus 2, the term is 0. So since there's kind of this ternary property instead of a binary property where you had the even and odd, here we have to worry about actually 3 terms. So what we're going to do is it's going to be the same process. We're going to take our power series, C sub n x to the n, and we're going to write it as a sum of the multiples of 3 plus the multiples of 3n plus the multiples of 3 plus 1 plus the multiples of 3 plus 2. Okay, and again, we do this because there's kind of a pattern that every third value in our sequence, every third value behaves similarly. So the ones that are C sub 3, 3 sub n, this is going to be the terms like C0 plus C3 x cubed. So let's see, when n is 2, you're going to get C6 x to the 6th and so on. Okay, so we could do it that way. Or actually, it just occurred to me, we don't have a closed formula here, so we don't need to do this. So sorry about that. So what I said is true, but we don't have to worry about that exactly. All we really have to do, let's go back up, sorry about that. All we really have to do is just think about our power series as C sub nx to the n, as n goes from 0 to infinity. So this is C0, C1x, C2x squared, C3x cubed, okay, and so on. I'm just going to write out probably an obnoxious number of terms here. C5 x to the 5, C6 x to the 6, C7 x to the 7, and so on. And now C0 we said was A, C1 we said was B, C2 is 0. So the x squared term is gone. Actually, C2, C5, and C8 were 0. So every third term there goes. And then C3, I have to go back up and look, we said was A over 6. So this is A over 6, x cubed. C4 was B over 12. Okay, is that right? B over 12. And then C5 is gone. C6 was A over, I just looked at it, 180. Okay, x to the 6th. C7 was B over 504, x to the 7. And again, if you like, what you can do is you can factor out, you can kind of separate this into the A's and the B's. So it's what I was doing before that I had erased, where you have the C sub 3n, C sub 3n plus 1, C sub 3n plus 2. So that's fine. But this is going to be A plus A over 6 x cubed plus A over 180 x to the 6th and so on, plus B times x plus B over 12 times x to the 4th plus B over 504 x to the 7. And the reason for doing that is that you can factor out the A and the B, and then you get these functions. You get 1 plus x cubed, 1 plus 1/6 x cubed. So it should be 1/6 x cubed plus 1 over 180 x to the 6th plus B times x plus 1/12 x to the 4th plus 1 over 504 x to the 7th, and again, with as many terms as you want. Okay, so it turns out that these are going to be your solutions to the differential equation y double prime equals xy. Now, these are not nice functions in the sense that they're not like the usual functions that you would study in Calc 1 or Calc 2, but this completely solves the problem in a certain sense, right? We wanted to figure out what are the functions that satisfy this differential equation, and it turns out that whatever those functions are, these are their power series representations. So that's what the functions are. Okay, so it does solve the problem, just it's not quite as satisfying as coming up with a closed algebraic solution, but it's still a useful solution, right? If we wanted to figure out what are some properties of these functions, we could do that. Okay, so anyways, so just for what it's worth. So this, I think, is a good thing. We just did our first power series example where this legitimately needed the power series method.